All right. So we're going to start with the problems portion of our friggin' packet. And to start, we're going to do the discrete electrostatics, which is, well, the electrostatics that don't require calculus. So first, we're going to start with a charging problem. So first, we have a rod has a net charge of negative 320 nanocoulombs, and we would like to find how many excess electrons the rod has. So we're given that the net charge is negative 320 nanocoulombs. And again, the prefix nano just means times 10 to the minus 9. So I can just rewrite that as 320 times 10 to the minus 9 coulombs. And then I can use that fact to see how many electrons divide into this number. Because just looking at our data table of constants, we're given the fact that one electron is worth 1.6 times 10 to the minus 19th coulombs of negative charge. So this division gives us our answer of 2 times 10 to the 12th excess electrons on the rod. So now we're going to bring the negatively charged rod with an excess charge of negative 320 nanocoulombs near a conducting sphere that's grounded, meaning charges can freely move, so we could actually get a neutral sphere to become charged. So I'll just draw my charge distribution real quick. And if there's negative charges on the rod, well, we know that it's the electrons that move. So in this case, the electrons are going to move into the ground because they're repelled by the rod. And if electrons are leaving the sphere, well, we must have an excess positive charge left over. And now we're going to cut the wire and look at what happens to the charge distribution in the sphere and figure out its sign depending on when we remove the rod. So first, we're going to look at what happens if we just cut the rope or the wire when the rod is close. So if I just cut the wire right now, clearly I'm going to have a positively charged sphere left over because I just have the picture in front of me. So if I just cut the wire right now, the picture is going to stay the exact same. So the sphere will end up positively charged if I just cut the wire right now. But if instead I move the rod very, very far away, the sphere doesn't feel the influence of the rod anymore. So then the electrons would come back to neutralize the net positive charge on the sphere to begin with. So the sphere would end up neutral if we just removed the rod beforehand. It would be like the rod was never there in the first place. So the sphere being grounded sort of erases any possibility of there sort of being a memory that the rod was even there in the first place if we remove it. So it ends up neutral, and it's not even polarized. It's like I just deleted the rod. All right, next up for Coulomb's law ratio. So two particles of charge Q are placed a distance r away from one another, and when that happens, they feel a force F. We want to find the new force if both charges are tripled in magnitude, and we quadruple their separation. So anytime that we have these sort of ratio questions, you need a formula that relates all of the variables that are changing. And here it's force, charge, and distance, so it's obviously just Coulomb's law. So we could write F is equal to K times Q divided by R squared. And then whenever I deal with a change, I always rewrite the problem, except I write a little prime symbol here. Oh, that's not what I wanted to do. I write a little prime symbol. And then I can write K times Q divided by R squared. And here's where I put in my multipliers. So I said I tripled both charges. So both charges, which are on the numerator, get multiplied by 3. And then I also quadrupled the separation. So the separation goes up by 4, but again, I have to apply that square from the denominator. So that leaves my new force as the numerator goes up by 9, but the denominator goes up by 16. So I don't get 9/16 of the original force F as my answer to this one. There's many other ways of doing it. I like this sort of multiplier approach. So now we have a classic Coulomb's law setup where we have charges on a line of different distances, and we want to find the net force on one of the charges. So in this case, we want to find the charge on the leftmost, or the force on the leftmost charge. So first, we see that anytime you have charges on a line, they're going to experience multiple forces. So the Q is going to experience an attractive force from the negative 2Q, and then it's going to experience a repulsive force from the positive 3Q. And actually, even though the 3Q is more charged, that increased distance, the fact that it's 3 times as far away, means that that contribution is going to actually be much weaker. So we definitely should expect a net force that's going to be attractive to that 2Q overall. And we'll see that the math reflects that. So we're just going to find the rightward force from the 2Q and subtract off the leftward force from the 3Q. We do have this extra distance to deal with, but it should be pretty clear to see that if we have D and 2D as our segment distances, the total distance between the Q and the 3Q would be 3D. So derive an expression for the net force on the leftmost charge Q, and we're going to answer twice, once in terms of K and once in terms of epsilon naught. So we're using the fact that the net force is going to be equal to the force from the minus 2Q. Oh, and I did it again. Oh, that's not good. From the minus 2Q plus F from the 3Q. And then we'll write Coulomb's law out for each of these. So Coulomb's law says that force from the minus 2Q would be, again, we just deal with the absolute values here. K times Q times 2Q divided by their distance, which was just D. And then we incorporate the direction as a unit vector. So this force is acting to the right because it's attractive. And then we do a similar thing with the Q being attracted to the 3Q, or sorry, being repelled from the 3Q, which is at a distance of 3D squared. So again, remember that we're squaring the entire distance term. And this time, this is a repulsive force, so it gets a negative I hat attached as a unit vector. And then working out everything in common units here, we'd get 2 kq squared over d squared, which is the rightward force in the I hat direction. And then we'd get, well, 3 divided by 3 squared is going to be a third, so I'd get 1/3 kq squared over d squared, and that would be acting in the negative I hat direction. And now we just simplify. So I have 2, which is 2, which is 6/3, minus 1/3, so I get 5/3 kq squared over d squared. And then we see that the positive term wins in this situation, so this would be in the I hat direction. So that's one solution. Or I could just replace the k with 1 over 4 pi epsilon naught and get 5/3 times 1 over 4 pi epsilon naught kq squared over d squared I hat. And no, I'm not simplifying this second term because I don't feel like it. College Board doesn't care, neither do I. What is it, 12? 5 over 12 pi epsilon naught, if we actually did that. And again, notice that at the very start, we knew that the increased distance was going to make it so the attractive force to the right was going to win. And we see that. Now we'll find the electric potential energy of the charges. Typical conditions apply of letting u be 0 at infinity. And we'll answer it 2 ways again. So potential energy says we're going to look at the energies of all the pairs of charges. So our expression for the electric potential energy of a system is U is equal to the sum over all pairs of charges. And potential energy between a pair of charges is K Q over R. And again, energy is a scalar, not a vector. So we actually do respect sign in this case, because we can have opposite charges which have negative energy, and again, we think of that as like an energy debt. So in this case, we have 3 pairs of charges to consider. So we could do the q and the minus 2q, which are separated by d. We could do the q and the 3q, which are separated by 3d. Or we could do the minus 2q and the 3q, which are separated by 2d. And now we just get to play the simplify and fraction adding game. So we'd get a negative 2kq squared over d plus a kq squared over d minus a 3kq squared over d. And again, energy is a scalar, so there's no direction here, but we do respect the signs. So we'd get two possible answers, one with Coulomb K and one with epsilon naught. So I see I'd have negative 5 for my negative terms, and I'd have a positive 1. So we just get negative 4 as our multiplier. So negative 4 kq squared over d. Or for epsilon naught enjoyers, we would get 1 over 4 pi epsilon naught times q squared over d. Or sorry, 4q squared over d. And I'll just leave that there like that. Again, we could simplify, but I'm just showing the equivalency between k and 1 over 4 pi epsilon naught, because sometimes people forget that we can easily translate between k and epsilon naught just like that. Oh, and I missed my negative on the rewrite here. There we go. And it should make sense that it's negative because we have this sort of central minus 2q charge, which is closer to the two positives than either the positives are to each other. So we should have a net attractive system, or it should be an energy debt. So now we'll look at field and potential by removing one of the charges. So suppose we remove the middle charge and we're left with this setup, and we want to derive an expression for the field and potential at the midpoint. So once again, electric field, this would be what direction would a positive charge like to move due to everything around it. So I'm going to color the plus q as blue. We also said positives are sources, negatives are sinks. So at the midpoint, which I judge to be about right here, that would be the E from the Q, because a positive charge would be pushed to the right, away from the positive. But then for the 3Q, same thing. It would also be a source pushing away. So a positive charge placed near the 3Q would go to the left. And I know that this one is going to win out because it's the same distance because we're at the midpoint, but we just have 3 times the charge. So this would be the electric field from the 3Q. So now we'll do the same thing as last time where we derive an expression. Again, anytime with vectors, we don't put sign in it. We just get the unit vector correct. So I know that my net electric field is just the vector sum of the Q and 3Q individual fields. Again, this is called superposition when we add two fields together like this to get the net. And electric field is just KQ over R squared. It's Coulomb's law, except divided out by a charge by definition. So we get KQ over R squared, and R would just be, we're at the midpoint, so if the distance is 3D, we just have that, so we'd get 3 halves D squared on the bottom. And this would contribute in the negative I hat direction, or sorry, positive I hat for the first charge, because we said it's to the right. So again, this is why it's important to draw the picture, so you know what unit vector to draw. And then, similarly, we just have a 3Q for our second charge. And this would have the opposite unit vector of minus I hat, because the 3Q would be pushing to the left. And now we can try to simplify this as much as we can. So, for our first term, we'd get 4/9 KQ over D squared in the I hat direction. And then for our second term, we'd get 12/9 kq over d squared, but in the negative I hat direction, so those would subtract. So we see that the left would win by 8/9 kq over d squared. And I stopped asking for the translation to epsilon naught because I imagine you get the idea by now. All right, now for the electric potential. So for the electric potential, this one is also easy because we get the electric potential is a scalar. So I can just add up all the individual electric potentials, which is given by kq over r. And again, this was like the electrical height, where positive charges are like creating hills and negative charges are creating valleys. So in this case, I just have a positive 1q at a distance 3/2 d from the point of interest. And then I also have a positive 3q at a distance of 3/2 d from the point of interest. And just by adding these two, we can see we'll get 2/3 kq over d plus 2 kq over d, which is 6/3. So 6 and 2 make 8/3 kq over d for our net electric potential. And again, notice that even though the fields tried to cancel, electric potential didn't, because electric potential only depends on the sign of the charge, and they're both positive, so both charges would be pushing up on the terrain, trying to make a hill. You'd only get negative potentials if you get some sort of a valley caused by negative charges. So now we'll try to label the spot on the x-axis where the field will be equal to 0. So again, it's important we want to find where the electric field is 0, not the potential. So I can draw my charges here. Where there is a q on this end, and there's a 3q on this end. And maybe we'll put our little midpoint right there. So we're just going to estimate where this point should be. So we said that at the midpoint, the electric field was not 0, or the force on a particle. The force on a particle is definitely not 0 at the midpoint because the 3q is stronger, so it's going to be able to impose its will. So that means that we need to increase the distance from the 3q and compensate by giving the 1q sort of less distance so it can have an equalizing force. So that means that the position of interest would be right here. So just somewhere closer to the q than the 3q. And again, we can see this here, where since both charges are positive, the fields will point in opposite directions, so we know it is between the charges somewhere. And the field must be 0, closer to the positive q, because you need less distance to make up for the lower charge. You could also just make the argument that if I place it right next to the 3q, it goes left. If I place it right next to the q, it goes right, so there's got to be a 0 spot somewhere. And now we'll calculate the approximate distance from the left charge where the field is 0. So we're going to say that this distance that we're after is equal to x. So this is the q, this is the 3q, and then we're looking for this special distance where the field is 0, and we're just going to call this distance x. And then, since our entire system had a length 3d, the remaining distance, since we have to add up to 3d, would be 3d minus x. And these distances will become relevant later. So, in order for the fields to cancel at the midpoint, or sorry, at the point of interest, the leftward field from the 3q has to exactly be balanced by the rightward field from the positive q. So these two fields have to be equal and opposite, and they have to exactly cancel. So we can write ourselves an equation that we just know that the magnitude of E from the q has to equal the magnitude of E from the 3q. And we just apply our expression for electric field magnitude, kq over r squared. So this time the q is located at this special distance x, and the 3q is located at the special distance 3D minus x. Because again, if we used up x of the 3D, then that means we have 3D minus x left that could go to that. So now some things cancel out, so we'd get a 1 over x squared is equal to 3 over 3D minus x squared. And now it's just an algebra problem. So what you could do is you could solve this in terms of d, so you know it's going to be some multiplier in terms of d. So if you just set d equal to 1 and use Desmos, you could get an approximate numeric answer. But again, the general step for this would likely just be square rooting both sides. So you could do something like 1 over x is equal to plus or minus square root 3 divided by 3d minus x. That's typically the step to do this here. There is a more clever approach involving ratios, where you'd know that since the 3q charge is 3 times more charged, it has to be root 3 times farther away. But either way, solving this equation, you'd get x is equal to 1 over 1 plus square root of 3 times d. Or if you solved this in Desmos, or sorry, 3, this should be a 3 on top. Three over 3d minus x times d. So you would solve the equation and get that. If you did solve this numerically using Desmos, you would get that x is approximately equal to 1.098 times d. And then, easier part, explain why there's no finite position where the potential's 0. So again, electric potential is like this sort of height. So if I think of what my sort of potential map would look like for this, well, we get a spike, a positive sort of hill. Of course, this would be infinitely tall at the Q, and then we get a sort of taller, stronger hill over there before decaying. So again, the height could only be 0 if you had these sort of valleys that were generated by negative charges. Or you could just do it mathematically and say it's about kq over r, and if you have no negative q, you can't get a negative, you can't get a 0 without a positive plus a negative. Since both charges are positive, they can only make positive contributions, the electric potential, so you're only adding positives together. It does go to 0 very, very far away when it decays, but we wanted finite positions. And then, as I did here, using the sort of 3D model, both charges make hills, so you can't get any valleys that form if you have hills only. So again, my black line here kind of represents the 0. You can only get a 0 if one of your charges was negative, creating a valley. All right, now a 2D example of Coulomb's law. We're going to find the net force acting on the top charge in this triangle. So in this triangle, we see that all the charges are positive. So on the top charge, we're going to get pushed directly away by both charges. So that would represent the net force. And then we could just kind of simulate what this looks like tip to tail, because we could draw sort of this picture, and we see that we would get a vertical net force, because the left and right components of this exactly cancel, so we do get a vertical net force here. I know my picture didn't really show it the best. Derive an expression for the net force on the top charge. So once again, we know that the net force is going to be equal to the sum of all of the k, q, q over r squared r hats. And I'm putting the r hat here because direction matters. So just writing Coulomb's law is always the first step. And then using our picture, we see that what we want isn't the full force of each. We actually just want the y component. So I just want 2 times the y component from one charge pair. because again, we have just the two y components adding together, just to show this. So again, there's my y components, and then my x components actually cancel. So I'd get a left force and a right force, but I'd get two up forces. So my net force will just be 2 times an upward force. And to actually extract that upwards force, using the fact that I can create myself a little triangle here with my forces, we see that what we really want is this sort of y component, which is opposite the 60 degrees. So I could just multiply by the full force and then tack on a sine of 60, because again, sine or cosine just extracts a component. So I'd get 2 times k. Both charges are q, so I get 2q squared here. The distance is just the triangle leg, s. And then sine of 60 is root 3 over 2. And this would be in the upwards direction. So then we can cancel our 2's, and we'd get our answer is just root 3 times kq squared over s squared, and then that net force is in the j hat direction. So that would be how we get our net force here. Because again, we just had to use symmetry. So again, there's nothing that told us the net force was in the y direction. We actually had to draw both vectors and see that, well, we have a left force and a right force. So those cancel. But we have two upward force components. And these are all equal magnitude. So we know that we could just cancel the x components. So I'm really just looking for the two y components. And you can even think of erasing the purple vector because we decomposed it. All right, lastly, we'll look at an energy example. So two charges are placed at rest. Is the electric potential energy positive, negative, or zero of the two charge system? Well, our expression for potential energy of two charges is just kq divided by r. So we see that the sign just depends on whether we have like charges or opposite charges. So like charges would repel automatically because we'd have matching signs, so that's positive. But negative charges, they want to be together, so to separate them costs an energy debt, so it's negative, like in this case. Opposite signs, negative potential energy. Then suppose we move the charges closer together by an external force, keeping them at rest the whole time. So it's really important that they're at rest. If there wasn't an external force, we'd get a different bar chart because they wouldn't have to be at rest. But some force is keeping them at rest. So this could be our plus and minus, originally separated by a big distance, and then the second bar chart could be our plus and minus separated by a small distance. So we see that the charges remain at rest in both times. So this actually means that there's no kinetic energy in either state. So I will not have kinetic energy in either state. So this is what's different than most problems we've done in this regard, because we kind of let the field just push the charges itself. But then we just have to figure out what happens to U. So the potential energy is inversely proportional to distance. So potential energy increases in magnitude the closer charges are. So either the charges will take more work to put in that position originally, or it'll take more energy to put in to separate them if they're attractive. So we know our energy is negative. So I'm going to put a small negative potential energy at the start. And then if we're getting closer together, our energy debt is increasing because it's going to take a lot more energy to separate these two charges now that we've brought them closer, because the Coulomb force is going to be much stronger between the charges now that they're closer together. So now we have to figure out this work done by an external force, which is quite a tricky concept for a lot of students, but we actually just use energy conservation here. Energy can't be created or destroyed, so if you have an energy bar chart that doesn't match, well, it means that there had to be some sort of external work that came into your system. So I see that my initial and final energies are different. So initially I just had these two bars of negative potential energy, but in the end it seemed that I gained two extra negative potential energy bars. So that actually represents my addition of external work. So these two bars right here, this actually represents external work. And this should also make sense because if you don't have external forces, the U bar might go down, but the K bar goes up. So we get no net change of the system. So there's no work done by external forces. But for the TLDR, or I guess Coulomb didn't listen, external work is just the difference in energy between the two states, total. So we see that we gained negative energy, so that must mean the work done by the external force had to be negative, since the total energy of the system becomes more negative. All right, so that's everything with discrete electrostatics, and then we'll move on to continuous.